Here's something that'll mess with your head a little. The phrase personal computer wasn't coined by a visionary in a garage or a Silicon Valley pioneer. It showed up in a 1968 Hewlett-Packard advertisement for a programmable calculator. Marketing named the revolution before the revolution even existed. Today, we're diving into Computer History Decoded Part 2, specifically how we got from mechanical gears and punch cards to microprocessors and the machines in our pockets, who the unsung pioneers were that made it happen, and how programming languages transformed computers from room-sized calculators into tools anyone could actually use. By the end of this episode, you'll have a real mental map of how computing evolved and why the path it took was anything but obvious. I've got someone here who's been deep in this history, so let's get into it. Walk me through where we left off and what the next big chapter looks like.
So the thing that's easy to miss when you look at computer history is that the conceptual groundwork was laid way before anyone had electricity to work with. We're talking about Charles Babbage in the 1830s designing what he called the analytical engine, a mechanical general-purpose computer that had a store for memory, a mill for executing operations, and could be programmed using punch cards.
Wait, punch cards in the 1830s?
Right, and Babbage actually borrowed that idea from the Jacquard loom, which used punch cards to control weaving patterns. So the concept of giving a machine a sequence of instructions through physical media predates electronic computing by over a century. According to the History Tools timeline, Babbage began designing the analytical engine in 1837 and kept refining it for the rest of his life. The machine was never fully built. It was simply too complex for the manufacturing technology of the time.
So Babbage had the blueprint, but not the tools to build it. That's almost tragic.
It really is. And what makes it even more remarkable is what happened around that same machine. Ada Lovelace, between 1842 and 1849, translated a memoir about the analytical engine written by Italian mathematician Luigi Menabrea. But she didn't just translate it. She added her own notes that specified in detail a method for calculating Bernoulli numbers with the engine. According to Wikipedia's History of Programming Languages, most historians recognize this as the world's first published computer program.
She wrote a program for a machine that didn't exist yet.
Exactly. And according to Science News Today, her notes described how instructions could be given to the machine using symbols, sequences, and loops, concepts that are absolutely fundamental to modern programming. She essentially invented programming as an intellectual discipline a full century before the hardware caught up.
That reframes everything. We think of programming as this very modern technical skill, but the core ideas were worked out on paper in the 1840s. So how do we get from Babbage's unbuilt engine to actual working computers?
The bridge is a few key figures and, honestly, a world war. But before we get there, even before Babbage, you have Gottfried Wilhelm Leibniz in 1694 designing what was called the stepped reckoner, a mechanical calculator that could add, subtract, multiply, and divide. According to the History Tools timeline, that was a groundbreaking achievement for the time. And then Thomas de Colmar invented the arithmometer in 1820, the first commercially produced mechanical calculator, which was actually used through World War I.
So there's this whole lineage of mechanical calculation that most people have never heard of.
And it matters because each of those machines was solving a real problem of its era. Merchants, traders, navigators, they needed reliable calculation. According to Life Sciences timeline, in the 1570s, the go-to computer for a merchant was literally a book of pre-made calculations called a ready reckoner. And those books were full of errors, which became a major motivation for Babbage to build something better.
Oh, that's a great detail. The whole thing started because people were tired of math books with mistakes.
Which is very relatable, honestly. But then you get to the 20th century and things accelerate dramatically. In 1937, Bell Laboratories scientist George Stibitz built what the Computer History Museum calls the Model K adder, named because he built it on his kitchen table. It was a simple demonstration circuit, but it provided proof of concept for applying Boolean logic to computer design.
He built it on his kitchen table. I love that.
And that same year in Germany, engineer Konrad Zuse built his Z2 computer using telephone company relays. Then in 1941, Zuse finished the Z3, and here's the part that really gets me. According to the Computer History Museum, he built it in complete isolation from developments elsewhere. No cross-pollination of ideas. He was working entirely on his own.
Wait, so one of the most important early computers was invented in a total vacuum? No collaboration, no awareness of what anyone else was doing?
Completely independently. The Z3 used 2,300 relays, performed floating-point binary arithmetic, and had a 22-bit word length. It was used for aerodynamic calculations. And then it was destroyed in a bombing raid on Berlin in late 1943. Zusi later supervised a reconstruction of it in the 1960s, which is now on display at the Deutsches Museum in Munich.
That's a wild story. A machine that advanced, built alone, then destroyed in the war. And Zuse also created Plankalkül, right? The first high-level programming language?
Exactly. According to Wikipedia's History of Programming Languages, Plankalkül was created by Zuse between 1942 and 1945, and it introduced key concepts like variables, conditions, and loops. It wasn't implemented at the time, but it was the first high-level programming language. The guy was operating on a completely different level.
Okay, I want to take a quick detour here because there's a story I came across that I think is genuinely funny. You know the word bug in computing? Where does that actually come from?
Oh, this is a good one. So, the Computer History Museum points out that the term bug was actually used as early as 1876 by Thomas Edison to describe problems in his inventions. But the famous story is Grace Murray Hopper in 1947, who taped a real moth into the Harvard Mark II computer logbook and wrote underneath it, "First actual case of bug being found,"
She literally taped a moth into a logbook.
as documentation, which is both hilarious and very on brand for someone who was a pioneering computer scientist. But the point is, the term predates her by 70 years. Edison was using it for the same reason. Something in the machine wasn't working right.
Okay, so we've got Babbage's unbuilt engine, Zuse working alone in Germany, Stibitz on his kitchen table. Then what? How does this all converge into something that actually becomes the computing world we know?
World War II is the accelerant. The need to break enemy codes, to calculate ballistic trajectories, to process enormous amounts of military data, all of that created massive pressure to build faster, more capable machines. And that pressure produced breakthroughs that would have taken decades longer in peacetime.
And Alan Turing is central to that story.
Absolutely. The Computer History Museum notes that the British bomb, an electromechanical device for decrypting Nazi Enigma communications, was conceived by Alan Turing and Harold Keen. Hundreds of Allied bombs were built to determine the daily rotor start positions of Enigma cipher machines, which allowed the Allies to decrypt German messages. That's computing in service of survival.
And then after the war, the technology doesn't just disappear, it gets redirected.
It gets redirected and it gets miniaturized. And that miniaturization is really the story of the second half of the 20th century. According to Wikipedia's History of Computing Hardware, the development of transistor technology, followed by integrated circuit chips, led to revolutionary breakthroughs. Transistor-based computers replaced vacuum tubes, making machines smaller, faster, and more reliable.
How dramatic was that shift? Like, what did it actually mean in practice?
Think about it this way. Early computers filled entire rooms. The transition from vacuum tubes to transistors to integrated circuits is what eventually made it possible to put a computer on a desk and then in your pocket. According to the Wikipedia hardware history, metal oxide semiconductor large-scale integration, MAOS LSI, enabled semiconductor memory and the microprocessor, which led to the miniaturized personal computer in the 1970s.
So the 1970s is really the hinge point.
It's the hinge point. According to Wikipedia's History of Personal Computers, the history of the PC as a mass-market consumer device effectively began in 1972 with the introduction of microcomputers. Before that, early personal computers, generally called microcomputers, were sold in electronic kit form in limited numbers and were of interest mostly to hobbyists and technicians.
Kit form, like you had to build it yourself.
You had to build it yourself. And then Apple comes along. According to the Computer History Museum, Apple was founded in a garage by Steve Jobs and Steve Wozniak in 1976, and it went on to revolutionize computing over and over, from the Apple II and the Macintosh to iTunes and the iPhone. That garage origin story is almost cliché at this point, but it's real.
And Hewlett-Packard also started in a garage, right? There's something about garages and computing history.
There really is. According to the Computer History Museum, David Packard and Bill Hewlett founded their company in a Palo Alto, California garage in 1939. Their first product was the HP 200A audio oscillator, which rapidly became popular test equipment for engineers. And here's the wild part. Walt Disney Pictures ordered 8 of the 200B model to test recording equipment and speaker systems for the 12 specially equipped theaters that showed Fantasia in 1940.
So HP's first big customer was Disney. That is not a fact I expected to learn today. Computing history keeps doing that. You pull on one thread and you end up somewhere completely unexpected.
But let's talk about Silicon Valley, because that origin story is also not what most people think.
Okay, why is Silicon Valley in California? I've always just assumed it was there.
So, according to the Computer History Museum's Silicon Engine timeline, in 1956, Bell Labs star scientist William Shockley left New Jersey and headed west to found his own company. His talented team soon deserted their, quote, mercurial boss to start Fairchild Semiconductor, and those innovative silicon chips spawned a vibrant new industry. Silicon Valley exists because one difficult boss drove away his best people.
That is genuinely one of the best origin stories in tech history. A bad manager accidentally created Silicon Valley.
And it's a pattern you see throughout computing history. The people who get pushed out or work in isolation end up building the next thing. Zuse working alone in Germany. The Fairchild team leaving Shockley. Jobs and Wozniak in a garage. There's something about being outside the mainstream that seems to produce breakthroughs.
That's a really interesting thread. Okay, let's shift to programming languages, because I think that's where the story gets really interesting for people who use computers every day without thinking about how they work.
So, in the 1940s and 1950s, coding meant writing instructions directly in machine language or assembly language, sequences of binary digits, zeros and ones, where every line was specific to a particular processor. According to Science News Today, this approach was accurate but extremely slow and error-prone. You had to think like the machine.
That sounds exhausting.
Wikipedia's History of Programming Languages puts it well. The limited speed and memory capacity forced programmers to write hand-tuned assembly language programs, and it was eventually realized that this required a great deal of intellectual effort, which is a very polite way of saying it was brutally hard.
So what changed that?
Fortran. In 1954, John Backus led a team at IBM that developed Fortran, which stands for Formula Translation. According to Wikipedia, the first manual appeared in 1956, and it became the first commercially available high-level programming language. The idea was to let programmers write in something closer to human reasoning rather than machine code.
So Fortran is basically the moment programming became something a human could actually do without losing their mind.
That's a good way to put it. And according to the Lember article on programming language history, this is the moment when programming stopped being purely mechanical and became linguistic. Coders began, quote, speaking with computers. Every generation of languages after that was about making that conversation easier, more powerful, more accessible.
And Backus also formulated the Backus-Naur form, right? Which described formal language syntax?
Exactly. According to Wikipedia's list of computer science pioneers, Backus led the team that created Fortran and formulated the Backus-Naur form that described formal language syntax. That syntax notation is still used today to define programming languages. His work in the 1950s and 60s is still structurally present in how we build languages now.
That's a long shadow to cast. Okay, and then there's the internet piece. Because computers becoming personal is one thing, but computers becoming connected is a whole other revolution.
And the foundation of that is ARPANET. According to the Computer History Museum's Internet History Timeline, in 1969, 4 institutions were connected on ARPANET: the University of California at Los Angeles, the Stanford Research Institute, the University of California at Santa Barbara, and the University of Utah. That network was the technical foundation for the Internet.
4 universities. That's where the internet started.
4 universities. And the concept that made it possible, digital packet switching, was independently invented by Paul Baran, who, according to Wikipedia's pioneers list, published a series of papers between 1960 and 1964 about dividing information into message blocks and sending them over distributed networks. That idea of breaking data into packets and routing them independently is still how the internet works today.
So the architecture of the internet was designed in the early 1960s, and it's still the architecture we're using.
Fundamentally, yes, and that speaks to how well those early ideas were conceived. The people building these systems were thinking about problems that wouldn't fully materialize for decades. It's the same pattern as Babbage and Lovelace. The conceptual leap comes first, the technology catches up later.
Let's talk about storage for a second, because I think that's an underappreciated part of the story. Like, what good is a computer if you can't store anything?
Storage is the unsung hero of computing history. According to the Computer History Museum's storage engine timeline, the evolution goes from simple punched cards to magnetic tape to CDs to thumb drives to the cloud. And here's a number that really puts it in perspective. With today's magnetic storage techniques, more than 1 trillion bits of data can fit into an area the size of a postage stamp.
1 trillion bits in a postage stamp.
And the early computers had essentially no storage by comparison. The Z3 had a 22-bit word length. We went from 22 bits to 1 trillion bits per postage stamp in less than a century. That compression of progress is almost impossible to fully grasp.
It really is. And the cost trajectory is just as dramatic, right? Because the whole point of the personal computer revolution is that these things became affordable.
According to Wikipedia's hardware history, the cost of computers gradually became so low that personal computers by the 1990s, and then mobile computers, smartphones and tablets, in the 2000s, became ubiquitous. That word ubiquitous is doing a lot of work there. We went from machines that cost millions and filled rooms to devices that billions of people carry in their pockets.
And Bill Gates actually said something about this that I think captures it well.
The Computer History Museum quotes him directly. "I think it's fair to say that personal computers have become the most empowering tool we've ever created. They're tools of communication, they're tools of creativity, and they can be shaped by their user." That last part is key, shaped by their user. That's what makes a personal computer different from every computing device that came before it.
And that idea of a computer shaped by its user, that goes all the way back to the definition of personal computer itself, right? Which has a surprisingly contested history.
Very contested. According to Wikipedia's history of personal computers, there are several competing claims for who first used the phrase. Yale Law School librarian Fred Shapiro traced an early use to that 1968 Hewlett-Packard advertisement. But there are also claims from Alan Kay in a 1972 paper, Stuart Brand in a 1974 book, MIT's co-founder Ed Roberts in 1975, and Byte magazine's first edition in May 1976.
So nobody can agree on who named the thing.
And in 1975, Creative Computing actually defined it formally. A personal computer is a non-time-shared system containing sufficient processing power and storage capabilities to satisfy the needs of an individual user. That definition is still basically accurate today, just at a scale that would have been unimaginable in 1975.
Okay, I want to zoom out for a second because there's something that keeps coming up in this conversation that I think is worth naming explicitly. So many of these breakthroughs happened in isolation. Zuse working alone, Lovelace writing programs for a machine that didn't exist, Baran developing packet switching before the internet was even a concept. Is that a pattern or is it a coincidence? I think it's a pattern, and it's actually one of the more counterintuitive things about computing history. We tend to think of innovation as collaborative, and it often is, but some of the most foundational ideas came from people working outside the mainstream, without access to what others were doing. Zeus had no idea what was happening in the US or UK. Lovelace was working from a translation of someone else's memoir, and yet they produced ideas that shaped everything that came after. There's something almost poetic about that. The people who couldn't see what everyone else was doing ended up seeing further.
And it raises a real question about how we think about innovation today. We're so connected, so aware of what everyone else is building, that genuine isolation is almost impossible. Whether that's good or bad for the next generation of breakthroughs is genuinely unclear.
That's a thought worth sitting with. Okay, let's also acknowledge the people who don't always get their due in this story, because computing history has a real gender imbalance problem.
It does, and Life Sciences Timeline explicitly tries to address that. Ada Lovelace is the obvious example, the world's first programmer, working in the 1840s. Grace Hopper is another. She's the one who taped the moth in the logbook. But more importantly, she was a pioneering computer scientist who shaped how we think about programming. And according to Wikipedia's pioneers list, Frances E. Allen developed bit vector notation and program control flow graphs, became the first female IBM Fellow in 1989, and was the first female recipient of the ACM's Turing Award in 2006.
The Turing Award is basically the Nobel Prize of computing, right?
Essentially, yes. And Allen won it in 2006 for work she'd been doing since the 1970s. The gap between doing the work and getting the recognition is its own kind of story in computing history.
Yeah, and that's not unique to computing, but it's worth naming. All right, so when you step back from all of this, the mechanical calculators, the wartime breakthroughs, the transistor revolution, the garage startups, the programming languages, what's the through line? What's the thing that connects all of it?
The through line is that every generation built on the last, even when they didn't know it. Babbage's ideas informed Lovelace's program. Lovelace's concepts informed how we think about programming languages. Zeus's Plankalkül informed Fortran. Fortran informed every language that came after. The computer performance timeline puts it well. The evolution of computers has not been a linear path of improvements. It encompasses diverse influences and interdisciplinary advancements.
And the interdisciplinary part is real. We've talked about weavers, musicians, mathematicians, military codebreakers, and Hollywood studios all contributing to this story.
That's exactly right. The Jacquard Looms punch cards became Babbage's input method. Disney's need for audio testing equipment became HP's first major sale. The military's need to break codes became the foundation for modern computing. None of these connections were planned. They emerged from people solving the problems in front of them.
Here's what this really comes down to, I think. We talk about the digital revolution like it was inevitable, like of course we were going to end up with smartphones and the internet and AI. But the actual history is full of machines that were never built, ideas that sat dormant for decades, and breakthroughs that happened by accident or in isolation.
And that's what makes it worth understanding. Because if you know that Ada Lovelace wrote the first computer program for a machine that didn't exist, you start to see that the gap between a good idea and a working technology can be enormous, and that the idea still matters. If you know that Silicon Valley exists because a difficult boss drove away his best people, you start to see how contingent all of this is. It could have gone differently at 100 different points.
And the people who shaped it weren't always the ones who got the credit, which is maybe the most important thing to take away.
The history of computing is not just a story about machines. It's a story about people, some famous, some forgotten, who looked at the problems of their time and imagined something that didn't exist yet. And then, sometimes a century later, someone else built it.
That's a genuinely powerful frame. And it connects back to where we started, that 1968 HP advertisement that named the personal computer before the personal computer revolution had even begun. Someone in a marketing department wrote those words, and they turned out to be describing the future.
Which is either very prescient or very lucky. Probably both.
Probably both. So here's the thing I want to leave you with. The next time you pick up your phone or open your laptop, you're holding the end result of a chain that runs from a baboon's fibula with 29 notches carved into it 35,000 years ago, through Babbage's unbuilt engine, through a moth taped into a logbook, through a kitchen table in New Jersey and a garage in Palo Alto, all the way to a device that can fit 1 trillion bits of data in a postage stamp-sized space. That's not just technology. That's the longest relay race in human history.
And the baton is still being passed.
And the baton is still being passed. That's it for this episode of Copilot Podcasts. If this one sparked something for you, go dig into the Computer History Museum's timelines. They're genuinely fascinating, and everything we talked about today traces back to sources you can explore yourself. We'll see you next time.